Hi, Arya, man. First of all, sorry about tonight. I'm just absolutely exhausted. So I just thought I'd give you a quick 5-10 minute run through of the things we covered last night, just so you've got something to look at tonight or maybe tomorrow. But I'll speak to you tomorrow anyway. So the first one is the small angle approximation. So before we go into that, I imagine school hasn't explained where they came from. It's actually a new concept at A level. That's why yesterday I was a bit like, no one's asked me that before. And that's because they've changed A level last year or the year before, and this is one thing that I didn't catch. They've put in, and no one's asked me about it, so I just didn't know about it until you asked me. So thanks for sort of updating me on that. Normally, small angle approximation and Taylor series is most definitely a university for first year of university level kind of concept, especially Taylor series. So this is what you are using, something called Taylor series, and what they are is that any function like e to the x, sine x, cos x, tan x, anything that's not a polynomial, basically like log x or combinations of them, can be written as a polynomial. What's known as an infinite series of a polynomial. So as you can see below, I've written out e to the x there. E to the x can be written, I know it's a bit weird and you probably wouldn't even look at this at A level, but just so you're aware that e to the x can be written as 1 plus x squared over 2 factorial. If you look up Taylor series, you can see where it comes from, and it's to do with uh, continuous differentiation, but you don't really need to know that for now. It's not going to change your world much or anything like that. But the idea behind it is that anything can be represented as a sum of polynomials, which is quite amazing, really, that if you add those functions together on the right, one, so a horizontal line across the across the graph, y equals 1, y equals x, so a line of gradient 1, and a quadratic divided by 2, x squared, and then a cubic divided by 6, and then x to the 4 divided by 4 factorial, so 24, and so on. If you add all those graphs together, they will combine to form e to the x, which is pretty amazing, really. Secondly, if you differentiate the right hand side of that, you'll get 1 plus 2x divided by 2, which is x, plus 3x squared divided by 6, which is x squared over 2, and so on. And you'll see that you actually get the same thing again, because derivative of 1 is 0, derivative of x is 1, derivative of x squared over 2 factorial is x, and derivative of x cubed over 3 factorial is x squared over 2. So we're getting the same thing again. So that's another proof that, sorry for my rubbish writing, it's another proof that the derivative of e to the x stays the same, because we're just going to get the same thing, even in this other format, which is pretty amazing. So the small angle approximations, I'll put on the next page. Now the reason they're called small angle is because there's two main reasons. One is that we're looking at the trigonometric functions and their Taylor series versions of them, so that, in other words, the polynomial equivalent of sine x. So if you actually add x and then add minus x cubed over 3 and so on, there's a pattern to it, which is odd numbers, odd powers, x cubed, x power 5, x power 7, and so on, and the signs change. If you add all those things together, you'll get a sine curve, which is pretty crazy as well. Same for cosine x, because it's the opposite, the numbers are kind of the opposite as well. So instead of being odd terms like x to the power 1, x cubed, x to the power 5, and so on, so that should be in a cube there. It's even terms, so x to the power 0, which is 1, x squared, x to the power 4, and so on. Sorry, I forgot to put a plus dot 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 dot. And they all go up to infinity, there's an infinite number of terms in them. But the smaller, the larger the powers get, if x is a small number, then effectively it becomes 0. So that's why I've included there x cubed on the sine x, x cubed over 3. If x is small, like 0.01, and I cube it, I'm going to get 0.00001, and dividing it by 3 makes it even smaller. So you can pretty much ignore it. So that's why, for small values, then we can just eliminate these things because it's too small. Yeah, and that's not why we use radians, but using radians, it takes all the way up to 57 degrees before we get to the number 1. So that's why they're really closely aligned up to about 45 degrees, because we're only getting up towards sort of 0.6, 0.7 there, and if you cube it, it gets pretty small, so we can almost ignore it. For anything smaller than 0.7, 0.01, it's going to just be 0, isn't it, effectively? It's like the same thing as differentiation, where you've got a little bit of x is squared, cubed, and so on. It's just too small to worry about. For tan x, same situation. The x cubed over 3 is just too small. It's not going to make any difference to us. For cos x, we can't just cancel out the second term, because the first term is just a number, and cos x is not equal to 1. So you can't approximate. That's not a good enough approximation. Just cos x is 1 all the time, because it's not. So that's why we need to have a second term in there to make it kind of do an error correction on 1. And the third term then is x to the power 4, so we can just ignore that, because if it's a small value, it's not going to do anything. It's practically 0. So that's why it's 1 minus x squared seems a bit different to sin x and tan x. That's why, because we can't just have 1. So we have the second term as well. I've actually put there to Google. It's worth your while just having a look at what the Taylor series of these trig functions are in full, and you'll hopefully see a pattern. Sin x and cos x are kind of the opposite of each other. Not surprising, is it, really, when you think about that's what they actually are. Height and width are opposites. And tan x is just sin x divided by cos x. And you can actually see that if you divide one by the other, they would cancel out, and you'd end up with tan x in that way. If you do Google it and read it through, it'll tell you how they're derived, and you'll see it through. It probably will seem a bit weird, but if you want to have a look through it, it's worth a look to see where they come about and where e to the x came from, and so on. So why do you need to know all this? You might be wondering. The reason you do this is because another new thing that A-Level's come along with is that you actually have to demonstrate the derivatives of functions from what's called first principles. So y, when you differentiate sine, you get cos. You need to know y, and you need to demonstrate y. And to do it with sine and cos and tan, you need to use a trick, basically, which is one is using compound angle formula, which you haven't done yet, so I don't really want to talk about that just yet. But the second trick is that you reduce those formula to small angles, because of course when you differentiate, we're going to let dx become 0, or become tend towards 0, and that's the same thing here, isn't it? We're trying to make the thing that's changing small, and so it's going to become it's going to make it 0. That simplifies the problem, and when you do it, sin x will become cos x, and so on. Cos x will become sin x minus sin x. But if you haven't done the compound angle formula, there's no point in me showing you that now, because it'd just be a bit too overwhelming for you. You need to understand that a little bit first, and then when you understand that, you can combine the two things. So I'll just leave it at that for now, so that you can see why it is you're being made to practice these kind of maybe what seems like abstract things, proving this is equal to that using a small angle. That's the main reason why, so you can demonstrate your differentiation, first principles. The other thing I wanted to talk about was partial fractions, and we talked about the 3 kinds. So what we're trying to do is undo algebraic fractions. Everything has a reverse, so if you do algebraic fractions, you get an answer, and then undoing that, we utilise the ideas of partial fractions. So just to quickly go over the 3 situations, because I went a bit all over the place last night, so here they are. The first situation is we've just got 2 straight lines multiplied by each other, so that's your normal kind of quadratic, alright, but in a factorised form, because remember, brackets also mean this is a factorised expression, and it's easier to deal with in that way. As you can see, not only could I cancel things if they're on top, I could also split them up into partial fractions. And that's what we do there. We're just trying to figure out what a and b were by multiplying both sides by x plus 1 and x minus 2. For situation number 2, we might have a repeated repeated factor, x minus 2 squared in this case. So this will be a cubic underneath, so on top we have 1 power less, so we have a quadratic. on top of there. Here we're going to have ABC, but we're going to have x plus 1, x minus 2, and x minus 2 squared. And remember I said that's because of it could be that when you're adding fractions, like a third and a ninth, you can change the 1/3 into ninths. And so it could be that you're using a factor of another. So if that's the case, we need to include both possibilities. So 9, you can think of this as x minus 2 being 3 and x minus 2 squared as being 9. Just because there's a 9 in there doesn't mean there wasn't a 3 in there originally, because that might have been there in the first place. And you do the same thing, multiply through by the denominator, x plus 1, x minus 2 squared. That'll cancel stuff out, and then good choices of x, clever choices of x, not just anything, use ones that will cancel out, so in letters. So you eliminate one of the letters, and try and figure out the others. For this one, x is 2 is going to be your first choice, isn't it? It's going to eliminate b and c, or two of the letters anyway, whatever they'll be. And the third one is when you've got a quadratic which isn't a square, so it's a rectangle, because we have to look at all the possibilities. So here we're looking at one where the quadratic is a square. Here we're looking at all the rest of the possibilities, which is it's a rectangle. And that's in some ways a little bit simpler, because just two things multiplied by each other, x plus 1 and the quadratic, so that's why we end up with these two. But because this is in a quadratic form and not and it's a rectangle, we have to have this extra x up there and it's plus c, because if you try and undo that, it's quite hard to show that numerically. But if you're trying to undo it and figure out where it came from, one of those two things must be true. They must have been there, right? But where it came from before, we'll have this extra x as well. So why do we do all these? Okay, so like I said yesterday, the reason we do partial fractions and undo algebraic fractions is we might be asked to integrate these, and this is actually quite painful to do. So if we can split them up into two easier ones, that's going to make our lives a lot easier. Do you know the integral of all these things? Do you know what the integral of a over x plus 1 is? There should be the x's on these, and all these, by the way. So I'll just leave them off for now for time, but they should all have the x on. Do you know what the integral of that is? And if you do, that means you can do all of division integration at A level, because essentially you'll never be asked to do anything more complicated than that. The tricky bit really is just the initial partial fraction bit, realising, okay, I need to put them in partial fractions, and then I need to integrate each one, and it hopefully will be easy for you. Again, hope that all makes sense. Please give me your feedback on anything I might have included or I shouldn't have left out, and I'll speak to you tomorrow.